So, now what we are going to do is we are going to use the Bayesian network to think about what are the conditional independence assumptions it is making, and how can I read the graph structure to figure out what conditional independences are being said by this graph, right. And graph structure of a Bayesian network reflects some conditional independences that the graph structure is saying, and there are some local semantics for it, and I will start by asking questions. Okay. The first question is John calls conditionally independent of earthquake given alarm? We have discussed this, but let us do this again. Is John call conditionally independent of earthquake given alarm? Yes. Is John call conditionally independent of burglary given alarm? Yes. Is John call conditionally independent of Mary calls given alarm? Yes. So, in fact, this is true, right. Once I know alarm, John calls is independent of everything else in this graph. Is there a general principle here? And the general principle is this: given my parents, I am independent of all non-descendants. Okay. So, in this case, my parent is alarm, I am John calls, and my non-descendants are earthquake, burglary and Mary calls. In fact, I have no descendants. So, everything else is a non-descendant. This and this gray thing shows that once these are all the nodes that have been cut off. Once I know my parents, nothing else matters to me, but my children still matter to me. That is also true in many families. If you want to understand about me, let us put it this way. If you knew my parents, you will be able to understand about me quite well. After that, my grandfather or other people do not matter. Now, this is not exactly true, because sometimes they say that some traits come from grandfather and grandparents, but that is how this is not for nature, this is for nurture. So, how my parents treated me depends on their parents, but once you know my parents, you do not need to go to their parents to understand me. They treated me the way they treated me based on who they are, right, and once I know who they are, then you can figure out who I am. So, in other ways, but my children still give information, because I am treating my children, and by knowing my children you will be able to understand more about me, but no other people matter. Okay. So, that is what this particular theorem is saying, that if a random variable's parents are given, right, they are known to you, then the node is conditionally independent of all the non-descendants, right, and we did one example. All parents must be given, good point. In this example, right. So, in this example we are talking about x. So, we are talking about x and the parents are u1 to um, thank you, I made a small mistake. So, x is the node here, its parents u1 and um are given. Now, it is conditionally independent of all the non-descendants. So, what are the non-descendants? Parents of u1, parents of u2, their parents, or zi's also. I am conditionally independent of the zi's also, right, but I am not conditionally independent of the yi's, which are my children. If I know about yi, I also get to know about zi, that is correct, but if I only additionally know about zi, but do not know about yi, that does not change my. So, think about it this way. See, what is zi? Zi is sort of my wife or my spouse, because we have a child together, if you think about it in human words, right. So, if you have not seen the children and if you only meet the wife, this thing is saying you can't tell about the husband. Now, this may or may not be humanly appropriate, but what is the intuition? See, the intuition is that zi and x may both be the reasons for why yi turned out in a certain way. If you see yi, you have to figure out, okay, is it because of zi, is it because of x? By knowing zi and y, I can explain y away by zi. Like for example, this is exactly that case where earthquake and burglary are the two parents of alarm, right. So, by knowing earthquake and alarm, do I know something about burglary? Yes. But otherwise, by knowing earthquake, do I know something about burglary? It is exactly the same setup, right. Earthquake and burglary are independent of each other, right. But by knowing alarm, they become dependent on each other. By knowing the child, the husband and wife become dependent on each other, because they are raising the child together. Now, the child may have turned out one way because of one parent or the other parent, and if the child has turned out one way because of one parent, then reduces my probability that it is because of the other parent. That is the analogy in our world. But forget the human world. I think this specific example will make sense to you. Earthquake and burglary are independent of each other, but given alarm, earthquake and burglary are dependent on each other. All non-descendants are independent given the parents, that is right. No, given yi means given the child. So, the statement does not say anything about what happens if the child is given. It is a very specific statement. It is saying that if I give you the parents and only the parents, right, then I am conditionally independent of my non-descendants, right. Okay, good. Let us do some more examples and we will come back to this. Will x dependent on this? Yes, it will, and we will come to that. We will do this in more detail, right. Give me a few slides and we are exactly going to come to that. Okay. How about this? Is alarm independent of everything given earthquake and burglary? Alarm is independent of everything given earthquake and burglary? Why? We just said that the alarm is, or a node is independent of the non-descendants given the parents. Now, are we given the parents? Yes, alarm's parents are earthquake and burglary. Are we asking only about the non-descendants? We are also asking about descendants. So, first of all, the theorem says no, but intuitively you all said yes. So, let us think about this. So, the question you always have to ask is, by knowing this thing, do I additionally get information about the variable? So, the question is, I already know earthquake and burglary, I know their values. By additionally knowing the value of John calls, does that change my probability distribution about alarm? That question you have to answer. So, let us think about it. So, suppose we can keep any value. So, let us say burglary happened, right. Or let us take an easier example, let us say earthquake happened, right. Now, the probability of alarm going off was about 0.29 at that case. Now, John called. Does that increase my probability that the alarm must have gone off? See, earlier I was weakly, it was weakly likely that the alarm would have gone off, 0.29. But now John has also called. Now that John has called, I have obviously increased my probability that alarm might have gone off. Or let us say both John and Mary called, then the probability has become very close to 1 actually. So, therefore, by additionally knowing John, even though I knew earthquake and burglary, I get more information about alarm, which basically means that they are not conditionally independent. I mean, you can do it in two ways. You can do this intuitive thinking. This intuitive thought is actually incredibly important. This is extremely important in the sense that you have to ask the question, if I also give you this variable, does that change my evidence? Does that change the information that I have about the variable at hand? But you can also apply the rule that given the parents, my node is conditionally independent of all non-descendants. So, non-descendants John Call is his descendant, so it is not conditionally independent. So, given earthquake and burglary, what is alarm conditionally independent of? Radio. Just additionally knowing about radio gives me no more information. Why? Because radio can only influence alarm. So, radio says that I heard on the radio that alarm has that earthquake has happened. So, what basically that says is that if I hear on radio, it can only influence earthquake, but I already know earthquake. So, radio would have affected alarm if I did not know earthquake, but now that I know earthquake, radio has no effect on me. Right? I would really strongly encourage you to do these kinds of questions at home, because the more you are able to ask the question, and this is exactly the words you have to use. I already know earthquake and burglary. By additionally knowing about this variable radio, do I get more information about alarm? This is exactly the way you should formulate the question, and then think about it, and the more you will think about it, the more it will get clearer. Now, yes.
It's saying like knowing that John Paul, and we already knew that earthquake and burglary have happened or not.
Have happened or not happened, yes.
Radio and John Paul, like in a way, similarly affecting.
Are radio and John Call similarly affecting alarm? So, the question is how are they affecting alarm? In one case, John Calls is a child of alarm. In one case, radio is not the child of alarm. So, they are not similarly affecting alarm.
Like if we know that radio news was there, then the probability of earthquake is okay.
The question is, if I knew about radio, that there is a news, the probability of earthquake has increased, but I already know earthquake.
So similarly, when John Paul already know about that.
No, we do not know about alarm. So, again, that is very important. What is given to us? We are given earthquake and burglary. Those two things are given to me, which basically means I do not have to estimate them. They are given, I know their values, I know whether it is true or false. I am interested in alarm, I am interested in whether my information about alarm increases or not. So, I do not know alarm, I am estimating alarm, and now I am asking the question that if I additionally tell you about radio, does that increase your evidence about alarm, decrease or remains the same? If I additionally tell you about John Calls, does that increase your evidence about alarm, reduces or remains the same? If it is increases or reduces, they are not independent. If it remains the same, they are independent. Okay, very good. This is important stuff. The more you ask, the more it will get clear. Now, the second theorem is, given Markov blanket, I am independent of all the nodes in the world. Like I am independent of everything given some set of nodes which are very close to me. That is my family. So, what is my family? My parents, my children, and believe it or not, yes, that is true, the other parents of my children. Now, of course, because this is a Bayesian network, you can't use the word wife or spouse or husband, right. So, you can say spouses, but then that reflects a different world, not the one that we currently live in, maybe the world we will live in, 10, some 1000 years later. Okay. So, what is my Markov blanket? My Markov blanket is my parents, because they consume all the evidence I am getting from my ancestors. It is my children, because they give all the evidence they give to my descendants, and also the other parents of my children, because they are also the ones that are affecting my children, and so that makes a collective whole. This is called the Markov blanket. So, let us ask some questions. Given alarm, is burglary conditionally independent of everything else? Given alarm, is burglary conditionally independent of everything else? What is the Markov blanket of burglary? Alarm and earthquake. So, therefore, the answer is no. Can you tell me intuitively what is going on? Why is earthquake important? Because alarm could also have been caused by earthquake. So, by knowing earthquake, I increase my or decrease my probability of burglary, right. So, if earthquake has happened, burglary's probability decreases. If earthquake has not happened, burglary's probability increases. This, however, is correct, right. So, by knowing earthquake and alarm, burglary is conditionally independent of everything else, right, because that is the Markov. So, now I think this is a good time to stop. we have done two theorems. One theorem is what happens given parents, one theorem is what happens given Markov blanket. Of course, you might be asking the question, given burglary, is John calls independent of radio? You can ask that question, and neither of the two theorems will apply, because neither is burglary the parent of John calls nor the burglary is in Markov blanket of John calls, right. So, in such a situation, how do we generally analyze a given Bayesian network? And that happens using a principle of D-separation. A Bayesian network structure represents several conditional independence assumptions. The structure itself encodes some independence assumptions, and one such independence assumption that we did was that given my parents, me as in a random variable, given a random variable's parents, a variable x is independent of all non-descendants. Descendants still matter, but non-descendants are independent given the parents. Okay. And the second thing we discussed is, given the Markov blanket, x is independent of all other nodes. And what is the definition of Markov blanket? The definition of Markov blanket is parents, children, and parents of children. So, other parents of the children. So, that is your closest family. Given your closest family, nothing else matters to you, you are independent of everything else. But of course, these rules are applicable in specific cases. In one case, if all your parents were given, in the other case, if all the Markov blanket nodes were given. You cannot make it reverse, that if one part of the Markov blanket node is not given, then the independence does not hold. You can't say that. It is only in one direction. Given the Markov blanket, you are independent of everything else. So, you might ask that in general, how do we test independence of a given set of pairs of nodes given some other variables, right. So, this is the general question, and the answer to this general question is the concept of D-separation. Okay. So, we will have to just basically follow the book, follow the rules, and if you are able to understand the rules, then you would be able to do this. It is very simple. It says first forget the directionality, okay. Forget the arrows, think of the graph as undirected. First step, an undirected path between two nodes is cut off. Cut off means information cannot flow, okay, from one node to the other node. So, an undirected path between two nodes is cut off if information cannot flow across one of the two nodes, and if information cannot flow, then they will be, if information cannot flow, then they will be independent. Why? Because what is the notion of independence? The notion of independence is that two nodes are independent if adding any new information about the first does not add any new information about the second. Now, if they can't influence each other, then obviously they will be independent, right. So, now the next step is two nodes are D-separated if every undirected path between them is off. So, there are two nodes, there are many paths that connect the two nodes, and if all of them are cut off, that means information cannot flow from one node to the other node. So, then they will be called D-separated, they will be separated in this graph. You can extend it by saying two sets of nodes are D-separated. So, if this is a set of nodes, if this is a set of nodes, they are D-separated if for every pair of nodes they are D-separated. So, A, B, C versus D, E, F, there should not be a valid information path from A to D, A to E, A to F, B to D, B to E, B to F, and so on and so forth. So, all pairs of them should be D-separated, and two sets of nodes are independent if they are D-separated, right, because information cannot flow. So, that is the general definition, that you have to look at what are the ways in which a node can influence another node, and if you are not able to find any such way, then they will be independent of each other, they will be D-separated. However, there are rules on when is a path considered cut off and when is the path not considered cut off, and that actually requires directionality. Okay. So, there are three rules to check if an undirected path between the two nodes is cut off or not, or if a path between the two nodes is cut off or not, and one of them is called the linear connection. Suppose I want to ask you the question between burglary, alarm, and John calls. Now, look at the structure that they create. They create a linear structure. Burglary is the parent of alarm, alarm is the parent of John. Now, the question you ask is, in this linear structure, when can information flow from burglary to John calls? How can it flow? It can flow only through alarm. If I give you alarm, are they independent of each other? We can answer it in two different ways. We can say, let us see, alarm is given to me. By adding information about burglary, does it change my distribution about whether John is going to call or not? No, because John just listens to the alarm and makes the call, right? Whether John knows the cause of the alarm or not, it really does not matter, right? So, by knowing burglary, I will not get a change in the distribution of John calls. Another way of saying this is, given my parents, I am conditionally independent of all non-descendants. So, which node should I apply this? John calls. Let us apply this at John calls. What are the parents of John calls? Alarm. Given my parents, that means given alarm. I am conditionally independent of all non-descendants. What are the descendants of John call? Nothing. So, it is conditionally independent of all nodes given the parent. However you see it, that is fine. Basically, you can recognize that if in this particular linear structure, A goes to B goes to C, information can flow between A and C only if we do not know B, because for information to flow from A, it needs to go through B, right. So, it influences B, because B changes, so that influences C, therefore, C changes. If you already know B, the path is blocked off, it is cut off, and so information from A cannot go to C. Any questions on the first case? Everybody okay? Everybody okay? Let us look at the second case. The second case is what is called the diverging connection, and for that let us look at this specific example. Let us look at the triple John calls, alarm and Mary calls. This is what is called the diverging connection because they share the common parents. So, from one parent there are two diverging edges to two other nodes. Okay. Now, we again ask the same question. How does information flow from John to Mary? How does it flow? Let us say John called and I know about the fact that John has called. Does that change my distribution about Mary calls? Without knowing anything, if John has called, that means likely that the alarm went off, and if the alarm went off, probability increases, then Mary calling probability also increases. So, therefore, I mean it does not have to be deterministic, but as long as you have a change in probability, it can decrease also, by the way, it is all fine. On the other hand, suppose I give you alarm, suppose I tell you the value of alarm. Now, does additionally knowing that John has called change my probability distribution of Mary calls? No, because both of them independently listen to the alarm and based on that make their decision. They are both dependent on the alarm. If I know alarm, they become independent of each other. So, this is what is called the diverging connection. In this diverging connection, I have a structure where B is the parent of A and C. And again we ask the question, when can information flow from A to C? The information can only flow through B. I as a child say something about my parent, and since I now know something more about the parent, that says something more about another child. And if I give you B, then this path is cut off, right. Any questions on diverging connection? Okay. So, now we come to the more interesting connection, and that is called the converging connection. Okay. And for converging connection, I will look at earthquake, alarm and burglary as my example. So, in this case, alarm is the common child of both earthquake and burglary. Now, let us ask the question, when can earthquake influence burglary? This is a very interesting question, and some of you must have figured this out, but others think about it. I will ask you two questions. Question number 1, is earthquake independent of burglary? Question number 2, is earthquake conditionally independent of burglary given alarm? You can answer intuitively, I do not mind, or you can use one of the theorems that we have studied, or you can think about the fact that this is earthquake and burglary we are talking about. You can do whatever you want, but let us talk about the first question. So, is earthquake independent of burglary? Earthquake is independent of burglary. Let us just think in simple terms. If I tell you that there is earthquake, that does not tell me that your house is being burgled, as long as we do not model the inside that there is earthquake, therefore there is frenzy, people are, have gone crazy and suddenly some people can make advantage of that situation. We have not used that particular thing. So, modulo that earthquake is sort of independent phenomenon, burglary is an independent phenomenon. Now, the interesting question, is earthquake conditionally independent of burglary given alarm? Does somebody not see this? Everybody says no, that is pretty impressive. Let us think about this. Alarm is given to you. Let us say there was an alarm. You can do it in both ways, as long as there is influence one way, it is fine. Let us say there was an alarm. The question you have to ask is, by knowing there is earthquake, does that change my probability distribution about burglary, and vice versa? Any one question is fine, they are equivalent questions. Suppose I tell you that there was earthquake, what does that tell you about burglary? The probability has decreased. There was alarm, something must have happened. Oh, earthquake happened. Therefore, oh, burglary probably did not happen. This is the chain of reasoning that will go on in your mind. Again, these are probabilistic statements, but the point is, by knowing that one of the parent is the cause of my self, the other parents become less likely in this case. In other words, this is a phenomenon called explaining away. It is a technical term. It basically says that if I have many ways of explaining something, I use one to explain away the phenomenon, and so the others now they are less likely explanations. So, in this particular case, look what is happening in the converging connection. So, earthquake and burglary are not independent given alarm, right, and this we need to generalize, and so I will make it one more step complicated. Is earthquake independent of burglary given John calls? Again, let us think intuitively. John has called. By knowing earthquake, does that change my probability distribution of burglary? It does. It is not independent. Why? Because John has called. There must have been an alarm, or at least that increases my probability of alarm. Because the probability of alarm has increases, I am interested in explaining that out. And if earthquake has happened, I have now explained it, my burglary probability goes down. So, therefore, by knowing John has called, now earthquake and burglary have become independent. So, this is this one interesting phenomenon where both the random variables were independent of each other a priori. Earthquake was living in its own life, looking at the earth's rock movement and causing tremors. Burglars were living in their own life, and they were just looking at which doors are locked and who have elderly in there, and happily making their burglaries. And suddenly, by knowing alarm, they have become dependent on each other. By knowing alarm, because they are two independent causes of the same effect, because such an effect may have occurred, they have now become dependent on each other. Okay? And so, this is called the converging connection. and the rule for converging connection is slightly tricky. So, we will look at A, B, C. A and B are both parents of B, A and C are both parents of B, but B has its own children also, let us say D, E and so on and so forth. So, the converging connection says, contrary to diverging connection and linear connection, that information can flow from A to C if we do have evidence either in B or in any child of B, because the children of B eventually change the probability distribution of B, and now that I have more information of B, information can flow from A to C. So, A and C are not cut off, they were originally cut off, but they become not cut off if I know B or any child of B. And again, if you get confused, go back to these set of rules. This is very, very crisp. I will ask you if a set of node x1 versus set of nodes x2 are independent of each other given evidence E. So, then you look at each pair of nodes, look at all paths between this pair of nodes and see if information can flow. If you find any one path where information can flow, they are not independent of each other. And in every path that you check whether information can flow or not, either you will use the linear connection at every step. You will be going down this path at every step, either it will be a linear connection or it will be a converging connection or it will be a diverging connection. Keep following those rules. And if you find that those rules still make this path information flow, then it is not deseparated. If the information cannot flow, you check the next path. If you find no such path where information cannot flow, then they are independent of each other. Okay? Try to do some practice, this is an important. If you think that this became too confusing to you, I will tell you the one person who explains it extremely beautifully is Daphne Koller. Have we talked about Daphne Koller earlier? Daphne Koller is a very famous professor who was a professor in Stanford. She is amazingly productive, prolific researcher. She has produced a large number of extremely successful PhD students who are faculty members in their own right. She also is a co-founder of Coursera along with Andrew Ng. Check out her video on how to compute the influence between probabilistic graphical models, but also if you ever get to the point where you take a full class on probabilistic graphical models, where you learn not only Bayesian networks, but other kinds of graphical models like Markov networks, dynamic Bayesian networks, conditional random fields. There are other kinds of networks, cycle graph, there are networks which are both directed and undirected at the same time. There are networks which handle actions like influence diagrams, etc., etc. All of those come inside this big area called probabilistic graphical model. So, there is a probabilistic model, but you are using a graph structure to arrange the joint distribution, and if you ever get there, you will have to read a book written by Daphne Koller. It is the Bible of probabilistic graphical models. Okay. So, now that we have discussed what are the conditional independence assumptions expressed by a graph structure, we will do the next important thing about Bayesian networks. So, now we are done with semantics. So, we were done with syntax earlier, now we have looked at the semantics, what does the network say, what does the probabilistic graphical model say, and that is called the semantics. And now we will talk about inference. Okay. So, that is what we will do in the next class, and we can stop here. Thank you.